So I'm going to talk about ongoing works that we are performing with Yves Colin de Verdière and with Luc Hillairet around the spectral analysis of sous-Riemannian Laplaciens and the concept of Weyl measure, on which we will spend some time. So let me maybe recall briefly the context and what we call a sous-Riemannian Laplacian. In what follows, we consider what we call a sous-Riemannian structure, which is a triple composed of M, a smooth connected manifold of finite dimension, N, D, which is a subsheaf of the tangent bundle of M, that we call the horizontal distribution. So in local coordinates, you are, let's say, in Rn, and D at the point Q is spanned by some vector fields, let's say M vector fields. In general, M is less than N. Okay? For instance, in R3, you are given at any point 2 vector fields. Okay? This is the so-called horizontal distribution. And we define a metric on D, on the horizontal distribution, which is defined, for instance, like this. Okay? Which is defined so that if x1 and xm are independent, then locally it is a G orthonormal frame of D. Okay. Okay. There is, of course, a more intrinsic definition, but I think that most of the audience knows very well this definition. So now we define a sous-Riemannian Laplacian associated with this structure and with mu, which is a smooth measure, a smooth volume, which is given on the manifold M, which is completely arbitrary. I mean that as soon as you are given an horizontal distribution with a metric G on it, and as soon as you are also given a smooth volume, then you can define the corresponding sous-Riemannian Laplacian that we could also denote by delta index G and mu, just to underline that it depends only on G and on mu. So the very general definition is to say that is in terms of the extension of the self-adjoint extension in terms of the Dirichlet integral. Here, G star is the cometric associated with G. And so let me give immediately more tractable definitions. So more tractable definition is this one. A sous-Riemannian Laplacian is the divergence of a gradient, exactly like in a Riemannian geometry, of course. So a divergence is always associated with some measure, as usual, as in Riemannian geometry. And the difference with Riemannian geometry is there, because instead of taking the Riemannian gradient, now you take the sub-Riemannian gradient, which is defined in terms of the sub-Riemannian metric, meaning that the sub-Riemannian gradient of some smooth function phi belongs, by definition, to the horizontal distribution. Yeah, okay. Okay, so we can take it as a definition of a sub-Riemannian Laplacian. Now, let's say in local coordinates, so if D is locally spanned by a G orthonormal frame x1, xm, as I said before, then the sub-Riemannian definition is this object, which is the sum of the squares of the vector fields, so more precisely the sum minus the sum, because it is a negative, minus the sum of the xi star xi, okay, so where xi star is the transpose in L2 of M endowed with mu. Okay, so the transpose of x is always equal to minus x minus divergence, okay, which gives you this expression, the general expression for a sub-Riemannian Laplacian. Okay, so it's a sum of square. Let's say in short, it's a sum of square of vector fields. Okay. Now, to go to spectral consideration. So let us assume that M is compact we do not always need this assumption, but for the moment it's simpler to do it. Then what is well known is that under Hörmander's assumption, or Shaw assumption, or Lie algebra generating assumption, which says that the Lie algebra generated by the horizontal distribution is equal to the whole tangent bundle of M, or the Lie algebra of all possible vector fields, horizontal vector fields, is maximal. Okay? So under this assumption, we know that this operator delta is hypoelliptic. Actually, it is even subelliptic. It regularizes functions in scales of Sobolev spaces, okay, with a certain rate. We don't need it. If M is compact, it has also a compact resolvent, and thus a discrete spectrum. So in what follows, we will choose an orthonormal eigenbasis, phi k, composed of eigenfunctions of delta, associated to these eigenvalues, which are indexed in increasing order. Okay? It is important, of course, to fix the sequence in the increasing order. Okay. And our objectives in our works with Luc and Yves is to study the heat kernel associated with such sous-Riemannian operators, sous-Riemannian Laplaciens, to try to derive local Weyl laws and micro-local Weyl laws for such Laplaciens, try to identify what we have called the Weyl measures. I will come to that point. Weyl measures that are, we can say, canonical sous-Riemannian measures that we will want to compare with objects that we already know, like pop measure. And we want also to establish what is called quantum ergodicity properties. I will explain during my talk. These are the objectives. Okay. By the way, there are many things in my talk that we can also claim, that we can also state for slightly more general operators, which are, I don't remember the name, Hörmander operators, but of the first kind, of the second kind. I never remember. Let's say Hörmander operators. So an Hörmander operator is a sum of square plus a possible drift plus something like C identity, where C is some smooth function. So a big part of what we say is also valid for such slightly more general operators, except that when we will talk about Weyl laws, of course, we will need that such an operator be self-adjoint. And of course, such operators are not self-adjoint in general. Actually, delta x here is a self-adjoint if and only if the drift part, x0, is given in the form of a sum of xi with coefficients divergence. Okay. And so in that case, delta x is exactly coincides, if I forget about the term identity, with a sous-Riemannian Laplacian. Okay. But for instance, for the heat kernel asymptotics, we are able also to state results for such operators. I will explain. Okay. Sorry for these slides, but I need some notations, which are maybe a bit technical, except for those who are very well acquainted with sous-Riemannian geometry. So given our horizontal distribution, which is a subsheaf of D, we define a sequence of subsheaves that is usually called the sous-Riemannian flag at the point Q. So you set D0, which is equal to 0, D1, which is equal to D, and then you set, let's say, D2, which is D bracket D, okay? D plus D bracket D, okay? You take all brackets of order 1, and then blah, 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 and then you iterate. So you define dk, which is the set of all possible Lie brackets of length less than k, okay? So you obtain a flag, the sous-Riemannian flag, which is a sequence. Salut Sylvain. Which is a sequence. I'm lost. It's your fault. Which is a sequence of inclusions of subsheaves, okay? What do we need to define? So let me define maybe the weights, what are called the weights, because it's an important concept. So the weight, how to define it very easily? Let's say that we take local coordinates which trivialize locally this subsheaf. So it means that if you take n1 coordinates along D, along the horizontal distribution, you define that these coordinates have weight 1. Then coordinates that are along brackets of order 1, along D2, are said to have a weight 2, and so on. Okay? So the weights measure the minimal length, let's say, of the bracket which is needed to reach a direction. Okay? It's almost this. And I will define, I will also need the concept, so what we denote in what follows by capital Q. Capital Q is the sum of all these weights. And it is well known that if the point is regular, meaning that the flag is regular, meaning that the dimensions of these subsheaves are locally constant. Okay? There is no singularity. So if the point is regular, then it is well known that this number coincides with the Hausdorff dimension, of the sub-Riemannian structure at Q. Okay. And also we say that the whole sub-Riemannian structure is equiregular if all points are regular. So if there is no singularity in the sub-Riemannian flag at any point. Okay. Another technical but very, very useful concept is the concept of nilpotentization of the sub-Riemannian structure. So how it goes. We have a sub-Riemannian structure which is a triple, MDG. You fix a point, Q0, which is arbitrary. And you want to define another sub-Riemannian structure which is attached to this point Q0. So we denote it with a hat. More precisely, as you say, with a hat index Q0, because, of course, the nilpotentization is taken at some point Q0. So what is the nilpotentization? It is also a sub-Riemannian structure, which is intrinsic, and which is defined as follows. Let's say M hat is, let's say, it's Rn. Okay? Just take Rn. Let us define the nilpotentization of the distribution at the point Q0. So it is the span of all nilpotentizations of the vector fields at the point Q0 that I'm going to define. So let me define it, by the way. So how do we define it? Locally, we assume that M is Rn with a chart. And more precisely, we consider a chart of what is called privileged coordinates. Okay? Did you have time to define what are? No, you did not do it. So I will assume that it is known. Okay? Because privileged coordinates are coordinates that are adapted to the flag, but not only. Okay? They are adapted to the concept of non-holonomic order, but I won't take the time of recalling what it is, because it's too long. But in such a chart of privileged coordinates, we have the concept of dilation. So a dilation is an homothétie, but with homothetic numbers that are defined, you see, in terms of the order of the coordinates. So you multiply each coordinate, as I said previously, by epsilon to the power the order of this coordinate. Okay? This is a dilation. Of course, if you are not in the sub-Riemannian concept, all orders are the same, and it is a usual homothétie. Here, it means that it is just an homothétie which is adapted to the specific structure of the flag. It's very intuitive. Okay. For instance, if you are going to the direction of a bracket of order 1, you need to multiply your coordinate by epsilon to the square, something like that. It's quite intuitive. Okay, and now you define the nilpotentization of a vector field, which is this object. Okay, you take the vector field, you take it in a chart, okay, so in Rn, you pull back it under the dilation, you multiply by epsilon, and you let epsilon tend to 0. Okay, you obtain a vector field that is, by the way, homogeneous of degree -1, which is called the nilpotentization of the vector field. Okay, and so this defines the nilpotentization of the distribution.
So is it some kind of linearization of the structure?
Yes, yes, exactly, but adapted to the sous-Riemannian flag. Yeah, this is exactly that. Yeah.
Is that some kind of local normal form?
No, not always. Yeah, but yeah, in some sense, yes. Yeah. Okay, maybe I will give some examples later. Okay, so now that you have defined the nilpotentized vector fields, you define accordingly the sous-Riemannian metric on this nilpotentization structure, exactly as before. Okay, there is a corresponding metric for which these vector fields are G hat orthonormal. Okay, and finally, you define also the nilpotentization of a measure. So if you are given a measure mu on the manifold M, you may also define an associated measure on the nilpotentization of the manifold, which is this guy. Okay, you pull back the measure mu under the dilation, and you divide by the volume, epsilon to the power q, and you take the limit. And by the way, the nilpotentization of a measure mu is always the Lebesgue measure up to some constant. It's a constant measure on Rn. Okay. Now, if we want to define the nilpotentization in a more geometric way, there are several ways, but let's say that a nilpotentization of a sous-Riemannian manifold is just an equivalence class under the action of sous-Riemannian isometries. It's a more proper way to define it. Okay. So now that we have two structures, what I forgot to say is that this nilpotentization structure exactly plays the role of a tangent space to the manifold. This is exactly the corresponding Riemannian tangent space, but in sub-Riemannian geometry. But there is a big difference. In Riemannian geometry, if you take two tangent spaces locally, they are isomorphic. This is not the case in sub-Riemannian geometry. You take two tangent spaces locally, and in general, they are not SR isometric. It is the case in low dimension, but not if there are moduli in the classification. So it's a big difference. Okay. And so what is quite natural, given the fact that we have some tangent space, we want to compare these two structures locally from the spectral point of view. It's quite natural. So let us introduce the heat kernels of our sub-Riemannian Laplacian here, and the heat kernel of the nilpotentized SR Laplacian. So for the sub-Riemannian Laplacian, the sub-Riemannian Laplacian generates a strongly continuous contraction, by the way, here, semi-group. Okay, it is self-adjoint, blah blah blah. It is non-positive, so it's a contraction semi-group. In the more general case of a Hörmander operator, it is not a contraction semi-group, but there is a strongly continuous semi-group. However, no problem. And you define the heat kernel. So a heat kernel is associated to the operator delta and to the measure mu, which is the Schwarz kernel of the semi-group. Okay. Now you do the same for the nilpotentization. You consider the nilpotentized SR Laplacian, which is just the sum of the square of the nilpotentized vector fields here. You can note, by the way, that there is no divergence because the divergence of a nilpotentized vector field is always equal to 0. Okay. So same thing, it generates a sonic group, and you consider the heat kernel of it. So the Schwarz kernel of this guy. We will denote it by E index blah blah blah, but very soon it will just become E hat, okay, when there is no ambiguity. Okay, by the way, you can note that since this structure has many homogeneity properties, the heat kernel itself, the nilpotentized heat kernel, is homogeneous. This is homogeneity. Okay. With respect to the dilations that I defined before. Okay, so now there is what we like to call the fundamental lemma, because it's very instrumental in order to establish Weyl laws in what follows. So in this lemma, we want to make precise what is the asymptotics as time is going to 0 of the heat kernel. So what we do expect, of course, is that it converges as time tends to 0 in some sense to the nilpotentized heat kernel. It's very natural. So here is the result. Here is the result. We claim that, so if you take an arbitrary point, I say arbitrary, I mean it does not need to be regular. So you take a point Q0, you take a measure mu on M, and we claim that T to the power Q divided by 2 times the heat kernel of the sous-Riemannienne Laplacian taken at T, and you see dilation with homothetic scale square root of T taken at X, same taken at X prime, tends as time is going to 0 to the nilpotentized heat kernel at time 1. Okay, and actually you even have an asymptotic expansion with functions aj that are smooth, and this expansion, this expansion converges on any compact of M. Okay, I mean you have it is you have convergence in a C-infinite topology. This is the case. And moreover, if the point Q0 is regular, then this expansion is also uniform, locally uniform, with respect to the point Q0, which is also very, very important to derive the local Weyl law, of course. Okay? Okay, so here is the result, the first result. By the way, so in this result, we do not need M to be compact. We can slightly extend it to more general Hörmander operators, like that. Okay, provided that either x0, the drift, is itself horizontal. A bit more than that, it must be a smooth section, D. Smooth being very important. So in that case, there is nothing changed. And you can even ask x0 to be a smooth section of D2, but in that case, you replace the limit here by another operator, okay, where this guy is the nilpotentization, in quotes, of this vector field, but in the sense of D2, you know, so it's not homogeneous of degree -1, but of degree -2. Okay. But we do not need that. Okay. It is just to mention that it can be extended. Let me just give an idea of the proof of this lemma, because the proof was quite painful. Before giving the proof, maybe some comments on it. In this result, you see that if you take, so here you see x and x prime are in Rn, which is the nilpotentized manifold. So let us assume that we take x prime equals 0. So in that case, it means that you look at the heat kernel along the diagonal. So in that case, what you find immediately is this equivalence. The heat kernel taken at time t along the diagonal is exactly equivalent to the nilpotentized heat kernel divided by the good power of t. Okay? And by the way, this equivalence is locally uniform near Q0 if Q0 is regular, which exactly gives, in what follows, the local Weyl law. And it depends smoothly, on Q0. Yeah. It's very important, absolutely. Wait. And by the way, this result, as such, exactly generalizes results obtained by Métivier in 76, or by Ben Arous in 89. But as you can see, we have a bit more, because we do not only give the expansion of the heat kernel not only along the diagonal, but also nearby the diagonal, in a neighborhood of the diagonal, because it is a delta square root of t of x here. Okay? So it is nearby the diagonal. And this fact will be important to derive micro-local Weyl laws. And also to treat singular sub-Riemannian structures. Okay. Now let me just give an idea of the proof, because the idea itself is easy, but details are so much painful. Okay. By the way, it is still not completely solid, but there are still some small details to be fixed. No, but it's nothing now, but it's okay. But okay, so the idea. Let us take a chart, okay, always a chart of local coordinates, so that locally we are in Rn. It is a usual notation. We define xi epsilon, which is equal to epsilon pullback of xi under delta epsilon. So this guy is by definition a vector field that tends to the nilpotentized vector field as epsilon tends to 0. And by the way, this convergence is also in C-infinite topology. It's a strong convergence. So we also set mu epsilon, which is the measure that converges to the nilpotentized measure. Okay? And we introduce the operator delta epsilon, which is this guy. So what is this guy? What is this guy? So you have delta here, which is in M, which is locally Rn. Okay, you pull back it under delta epsilon, and then you multiply by epsilon square. Okay? So you obtain immediately this operator, which is the sum of the squares of the vector fields xi epsilon. And so what you see immediately that this operator exactly converges to the delta hat, to the nilpotentized Laplacian. Okay? Okay, so since you have such a convergence, which is a convergence in C-infinite, by the way, Trotter-Kato theorem tells you that the associated semigroups converge, but pointwise in L2. And thanks to this pointwise convergence, what you can say for free is that you have a convergence of the heat kernels in spaces of distributions. So you have a very, very weak convergence of heat kernels. This is not what we want. We would like, at the end, to have a very strong convergence like that. So how to do? So you use the fact that it is a Montel space. So it means that if you are able to give a uniform bound on those guys, then those guys are in some compact, and so weak convergence becomes strong. Okay. So in order to prove that the heat kernels epsilon are uniformly bounded in C infinite, the way we did it is to prove that the semigroup associated with delta epsilon is, in quotes, locally uniformly regularizing. A semigroup associated with a Laplacian is uniformly regularizing. I mean, it maps any Sobolev space locally to any other Sobolev space locally. And we want to do it uniformly with respect to epsilon. So to prove that, we have to come back to the proof of local sub-elliptic, sorry. This is a sub. You have to establish uniform local sub-elliptic estimates, as did Ormander, actually. Exactly as did Ormander. And to do that, by the way, we followed the proof by Kohn. We followed, rather, the proof by Kohn of Ormander sub-elliptic estimates.
Sub-elliptic for the heat equation?
Yes.
Not for the Laplace. It's the operator knows the heat operator.
Yeah, but it's the same.
Okay,
Yeah.
scalar,
Yeah. You are right. You are right to say it.
still, I do.
Sub-elliptic is given estimates for such a kind of operator. Actually, we are able to do it with a drift, and then we take rather as a drift d over dt, maybe with a minus. Okay. And so we get estimates for the heat equation. Okay, so this is the idea of the proof. Of course, details have to be written. And at the very end, so what is the relation? What you also have to understand. What is the relation between this operator delta epsilon, which is a pullback multiplied by epsilon square, and the operator delta? You see, it is just a simple change of coordinates, and so you have this relation exactly between the kernels. You have between the kernels a relation with coefficients that are, by the way, exactly the same as the homogeneity for nilpotentized heat kernels, and blah, blah, blah. Okay. Yeah. Then you take S equal 1, epsilon equals square root of t, and you get the result. At least you get the limit. You get the equivalent. Now to get a full asymptotic expansion with respect to epsilon, we have followed exactly the same method as did Davide in one of his papers. That was, by the way, a big source of inspiration to us. Where is Davide? Oh, yeah. So you were inspiring. So what we do is simply to write the Duhamel formula. Okay, we want to compare the semigroup associated with delta hat with the semigroup associated with delta epsilon, which is a perturbation of this Laplacian. Okay, so we write the Duhamel formula, and then we follow the fixed point argument. We iterate the formula, but so we obtain a series, an expansion of the semigroup, of the perturbed semigroup, with operators here that are some convolutions operator. Okay, and then you, once you have written, at least formally, once you have written this expansion, you take the Schwarz kernels and you obtain an asymptotic expansion exactly as in the lemma. Okay. And also another tool that we need, which is very, very important in order to lead all these reasonings, because all these reasonings are local, as I said. You take a chart and blah, blah, blah. But then you need a result which is very important in order to claim that actually the asymptotics of the heat kernel, that is a priori a global object, is actually purely, solely local. Okay? It is very important, of course. This is CAC principle, by the way. CAC principle of not feeling the boundary, meaning that from the point of view of the heat kernel, if you are there, then asymptotically with respect to time, you do not feel what is over there. It is very instrumental to have this, this beautiful lemma. Okay. Okay, so now from this instrumental lemma, let us take it to define a new canonical sub-Riemannian measure. Okay, so let me switch on a quite general question in sub-Riemannian geometry, which is the question, the very interesting question of trying to define intrinsic volumes in a sub-Riemannian manifold. For instance, this question was very much well studied and underlined by Andrei, Davide, and Hugo in their paper Calculus of Variation in 2012. So, for instance, one measure was very much studied, which is the usual Hausdorff measure, either the standard one or the spherical one. It was studied very much in many papers since the birth of sub-Riemannian geometry. Okay. At the beginning of the years 2000, there was a new measure, which is very natural, which is the pop measure, which is associated to the sub-Riemannian flag. I will recall it. It has been defined by Montgomery, and Pop, Octave Pop, I think, was one of his students, but he didn't remain in research, actually. But what a beautiful name, no? Pop. So there is the concept of pop measure, which is an intrinsic sub-Riemannian volume, which is very much useful in sub-Riemannian geometry. And here, in what we did, actually, we will propose a new one, which is the Weyl measure, which is of a spectral nature. We are going to define it. Okay. Oh, by the way, maybe let me do a remark. Concerned with nilpotentizations of measures. So if you take mu and nu, two Lebesgue measures on M, so you assume that mu is equal to h nu, so you assume that h is the density of mu with respect to nu. Then if you go to the nilpotentization, what you obtain is that mu hat is a constant Lebesgue measure on Rn, okay? Nu hat also, and the coefficients that is in between is exactly h taken at the point q. Okay? So going to nilpotentization is always very easy. Okay, so let me recall what is, or maybe not what is pop measure, but its main properties. So the pop measure is a canonical, so it's a canonical smooth volume form that is canonically, intrinsically associated with the flag structure, and of course with the sub-Riemannian metric. It is just a push forward which comes from the flag and from canonical surjections, these ones. Okay. I do not want to go into details, but it's a natural measure associated with the bracket structure of the sub-Riemannian manifold. So what are these the properties of pop? So pop is invariant under sub-Riemannian isometries, either local or global, by the way. Pop is in some sense doubly intrinsic in the sense that it commutes with nilpotentization, meaning that if you take the nilpotentization of pop at a point q, then it exactly coincides with the pop measure associated with the nilpotentized sub-Riemannian structure. Okay? So in some sense, it's doubly intrinsic. And also, pop is smooth in the neighborhood of any regular point. Okay, so an explicit expression of pop in terms of structure coefficients, for instance, was given by Davide and Luca in their paper in 2013, but in the equiregular case. But actually, the construction can be done as well at a singular point, and there is no problem. I'm not sure of the interest, but it can be done exactly as well, keeping all these properties. Okay. Now, how do we define the Weyl measure? So the Weyl measure will be of a spectral nature. So we consider our sous-Riemannienne Laplacian. As I said before, we diagonalize it. So we consider a fixed orthonormal eigenbasis, okay, with the eigenfunctions indexed in the increasing order. To do that, of course, here I assume that M is compact. We define the spectral counting function, which is capital N of lambda. So the number of all eigenvalues that are less than lambda. And the definition of the Weyl measure is exactly this guy. So what do we take? What do we take? We take a Césaro sequence, exactly here. You take the Césaro average of the phi k square times the measure mu. So you take partial sums, and you divide by capital N of lambda. So it is exactly a Césaro mean. So this guy, if mu is a probability measure, this guy is also a probability measure. And you take, if it exists, you take a weak limit of that. So it's also a probability measure. Okay. Did we define it as a? Yeah, I forgot. Actually, I forgot here to.
No, because pk square mu is a probability measure.
Ouais, voilà.
So
Oui, voilà.
you don't need mu.
No, I do not need mu to be a probability. It's stupid. Yeah, thank you. Yeah, it's a probability measure. Okay. Okay, so here is the definition of the local Weyl measure. Here, in this definition, I assume that the limit exists. It's not obvious that the limit exists. Okay. So if the limit exists, the Weyl measure that we will denote by small w index delta does not depend on the choice of the orthonormal eigenbasis, because it's a trace. It is invariant under sous-Riemannian isometries. It's almost obvious. And what we are able to prove, it will come in my further slides, is that in the equiregular case, it always exists. It is smooth. Does not depend on mu. And it also commutes with nilpotentization, like pop. I put quotes here because how to define this guy? How to define the Weyl measure associated with sub-Laplacian on Rn. Rn is not compact. So we need to do something here. We need to replace. We did not fix that, to be honest. And then it works, yeah. But there is another way, but okay. We can just replace the spectral function by the spectral density, and it should be okay. But okay. But it will also result from the explicit expression of W delta, actually. So okay. So here is the definition of the local Weyl measure. Now, we also define the microlocal Weyl measure, which is a lift of the local Weyl measure, which is on M. So the microlocal Weyl measure, which with a capital W. So this time it's a probability measure on the cotangent bundle, the unit cotangent bundle, which is defined. So exactly the same, except that you have to replace the operator of multiplying by a function f by any operator, any pseudo-differential operator of order 0. Okay? So you consider a quantization up, consider a symbol A of order 0. Okay? You consider these scalar products, and you make up exactly the same, the Césaro mean of these guys, and you take the limit. Of course, if you take a symbol A is some function of x and of p, the adjoint. Okay? So if you take a function A which is on x only, then you recover exactly this definition, of course. So it means that the push forward of the microlocal Weyl measure, when it exists, under the canonical projection is always equal to the Weyl measure, of course. Okay. So what we are able to prove here in full generality is that if it exists, the microlocal Weyl measure is always supported in the annihilator of D, always. Okay. So D perp is the annihilator of D. We like to denote it by sigma.
Except in the Riemannian.
Oh yeah, sure. Should have written it. Yeah. Oui, oui, bien sûr. Hein. Bien sûr. Oui, oui. Yeah, yeah. In the strict sous-Riemannian case, the microlocal Weyl measure is always supported in the annihilator of the horizontal distribution. So, of course, a general question that is interesting is to try to identify what is the Weyl measure, what is the microlocal Weyl measures, and try to compare them with the existing ones that are Hausdorff and Pop. So let us do it. Let us do it. Or maybe we can mention that for the microlocal Weyl measure, it's exactly related via a Fourier transform to what is called the averaged correlation of eigenfunctions. Okay.
Sorry.
Oui.
So you introduced the unitary Untitled Lemma.
Oui.
Is it defined?
The sphere is the bundle of half lines.
Yes.
You take the quotient under homothesis.
Exactly the same because it's a cylinder.
Okay. But is the orthogonal inside? So the orthogonal is not inside.
No, it's for the duality between tangent and cotangent. And it's a set of covectors which vanish on the distribution.
You take it because symbols are homogeneous, simply. It's by homogeneity that but you can forget about S. We don't care. Okay. Oui. Yes.
What happens in the Riemannian case? So what is this Weyl measure in the Riemannian case?
What is? Sorry?
The Weyl measure in the Riemannian case.
Simply the canonical volume, Riemannian volume. Normalized, yes, of course. Yeah.
Okay.
Yes. Okay. So now let me make precise what is the local Weyl measure in the equiregular case. Oui.
In the Riemannian case, you can still define delta G mu for any mu, and in
Oui.
any case, the Weyl measure
This guy.
will be the Riemannian volume, independently of the choice of mu for all those operators. It is independent of mu.
That's general, you said.
That's general. That's general.
It is general, yes. Yeah.
Just associated to the sous-Riemannian mu.
Yeah.
Like Pop or so you can compare.
Yeah. Mu plays no role when you go to the limit finally. Okay, so in the equiregular case, so meaning that the flag is not singular everywhere. So in that case, the Hausdorff measure is constant. We will simply denote it by Q. Okay. So in that case, what do we do? So we consider at any point Q, we consider the associated nilpotentized sub-Riemannian Laplacian, which is this guy. We denote by E hat Q, which is the heat kernel associated with that guy, and let's say with the Pop measure. Okay. Because it's canonical, so why not use it? Okay. So what we have seen in the fundamental lemma is that T to the power Q half times the heat kernel along the diagonal. This guy converges to the nilpotentized heat kernel, E hat. And this convergence is smooth and uniform with respect to Q. So you obtain immediately this result here. Okay? you obtain this result. And this result, now, if you write that this guy is a trace of some operator, of the heat-summing group, if you take an inverse Laplace transform, which is the Karamata theorem in that case, you obtain exactly the expression of the local Weyl measure. You obtain that the local Weyl measure has, with respect to pop, this density, which is the nilpotentized heat kernel at the time 1, but taken at Q. Okay? So this is the local Weyl measure. So it exists always in the equiregular case. It is smooth, and here is the guy. And also for the Weyl law, so the number of eigenvalues, so capital N of lambda is equivalent, up to some constant, to lambda to the power q half. So for instance, in the 3D contact case, in that case you have capital Q, which is equal to 4. So capital N of lambda is something like a constant times lambda 2. And constant that is equal in that case to I don't remember. Yeah, okay. So, but we have it. Okay. Okay. And so what we can say, by the way, from this expression is that in general, the local Weyl measure does not coincide with Hausdorff and does not coincide also with pop. So it does not coincide with Hausdorff. It's exactly the same argument as in the paper by Andrei, Davide, and Hugo, because Hausdorff is not smooth, whereas Weyl is smooth. Okay? And why does it differ from pop in general? Just because this function of Q here may not be constant. And by the way, we can easily give some cases where the Weyl measure coincides with pop. It coincides with pop if and only if this function is constant. Okay, so when is this function constant? So always from this paper where this was classified, this function, which is the nilpotentized heat kernel taken at Q and at the time 1 along the diagonal, this function of Q is constant, for instance, if the sub-Riemannian structure is free, or, for instance, in a low dimension case. So it's always the case when the dimension of the manifold is less or equal than 5, except one case. For dimensions of M lower than 5, we know all normal forms of nilpotent equiregular sub-Riemannian structures, and only one of them involves a modulus. This is the so-called, I did not write it here, but this is the so-called B-Heisenberg case. Le cas de contact 5D, oui. 5D, oui. Oui, oui. The B-Heisenberg case. In this case, we have moduli, and in that case, this function is not constant. So in that case, Weyl differs from pop, for instance. And it's even possible to compute it and to compute the density and how it moves. Okay. For the 3D contact? No? In the 5D case, we computed it. Yes. We have the expression of the density. Yeah. Mm-hmm. Mm-hmm. Yeah. It's some series. Depending, on the ratio of eigenfrequencies. Yeah, exactly. Yeah. A kind of zeta function, yeah. Mm. Mm. Only in the 5D case we have it. Okay. And concerning the microlocal Weyl law in the equiregular case, so we also compute it, but in the equiregular case. So what we can prove is a result that is more precise than the general lemma I gave previously. Now, previously I told you that the microlocal Weyl law is always supported in the annihilator of the distribution. Actually, we can say more in the equiregular case. You consider the annihilator not of D, but on the further subsheaves in the flag. Okay? And you take the subsheaf in a flag which is just before going to the tangent bundle, the last possible one, okay? Which is sigma r minus 1. R is the degree of non-holonomy, okay? The highest possible length of Lie brackets that is necessary, okay? And what we prove is that the microlocal Weyl measure is supported in the annihilator of that guy, which is much smaller, okay? So it shows that spectral concentration occurs where Lie brackets have the highest length. This is what it means in words, in simple words. Okay, and we can give an expression in terms of Fourier transform, but I won't spend time about that. Okay, and by the way, just because things are have to be fixed in our forthcoming paper. In the equiregular case, we can also define as well Weyl and microlocal Weyl measure in terms of trace, like that. Okay. We have many phone calls for that. Okay. Okay. Now let me. May I take just 3 minutes, maybe? Okay, thank you. Let me give some partial results for singular sub-Riemannian structures, so non-equiregular. What happens when the flag has some singularities? So for instance, let us consider a very celebrated case, which is the Martinet case. So Martinet case is on a three-dimensional manifold. Okay. You assume that you have a codimension 1 horizontal distribution such that, so D3 is equal to the whole Tm except along a Martinet surface. No, sorry, what did I? No, the contrary. D2 is equal to the whole tangent bundle except along a surface which is called the Martinet surface.
It's contact outside.
It's contact outside the Martinet surface, exactly. It's better to tell it like that. We also assume that there is no Martinet singularity. Okay. Okay, but the local model of the one form generating the Martinet case is exactly that guy. This is because of the square here that we have a singularity and a Martinet surface. So we can compute pop, of course, for this local model. This is pop outside of the Martinet surface. This is pop along the singular surface. Here, yes, it's a purely local model in which the metric is trivial here. Yeah. Just to give it was just to underline that pop measure is not smooth here, of course, and the singularity of pop is, let's say, 1 divided by a local equation of the Martinet surface. We could say it like that. The Martinet surface is locally given by phi equals 0, and in that case, pop is just a 1 over phi times blah, blah, blah. A smooth measure. Okay, so what we are able to prove in that case is that the local Weyl measure is exactly equal, so is supported on the Martinet surface, and it is equal actually to the pop measure restricted to the Martinet surface up to normalization. Okay, so again, spectral concentration occurs at singularities in some sense. Okay, and for the Weyl law, so what is interesting here is with respect, for instance, to the 3D case, there is occurring a logarithm of lambda here. So the Weyl law is lambda squared times the logarithm of lambda. Okay. And we can even compute a two-terms expansion of the heat kernel. Okay. Where you can see appear the logarithm here. Okay, and it is in accordance with what we expect, because if we take a function f which is 0 in a neighborhood of the Martinet surface, then this first term disappears, and you find again that the Weyl measure coincides with the pop measure outside the singular surface. Because outside of the Martinet surface, we are in the contact case. Okay. And here is also another singular structure, which is also well known, which is Grushin, the Grushin case. So the Grushin case is actually an almost Riemannian structure on a surface, on a 2D compact manifold. So almost Riemannian means that you have, where did I write it? Where did I write it? I did not write it. Okay, so it's Riemannian everywhere except along a curve, except along a submanifold of dimension 1. Okay, and in that case, we have a result that is exactly similar to the Martinet case, saying that, so this singular curve is denoted by S. The local Weyl law coincides with pop restricted to this singular curve. And the local Weyl law, the Weyl law, sorry, the asymptotic of the Weyl law is lambda logarithm of lambda. So again, it appears a log lambda. Okay. We also are able to give, in that case, a two-terms expansion of the heat kernel. And that's all for the moment for a singular structure. We would like to be able to continue. Yeah, I tell it at the end, but maybe I will not have time to develop it. Yeah. That's the only cases that we are able to treat for the moment in the, I have to stop, in the singular case. We would like to obtain more general result, maybe probably using the concept, of equi-singular sub-Riemannian structures. So a kind of stratification, but for the moment we are not able to do it. Okay, so let me stop. Let me switch actually the part concerning quantum ergodicity. I'm sorry for that. Actually, what we have obtained, but most of you already have heard some of us. In the 3D contact case, we have much more precise results. We have normal forms, and we are able to derive quantum ergodicity properties of the sub-Riemannian Laplacian in the 3D contact case under the assumption of the ergodicity of the Reb flow for the pop measure. Okay, but I don't have time to speak of that. Okay, so just several open questions. So as I said, we would like to be able to at least to prove and maybe to compute this new canonical measure in some more general singular cases. That's an open, completely open for the moment perspective. Also, by the way, we have no result for the moment on the microlocal Weyl law, except if the horizontal distribution is of codimension 1, because in that case it's an obvious lift. We have, oui.
Sigma R minus 1
Ah oui, tu as raison.
c'est line bond.
Yes, oui. Yeah. Yes, indeed. Yeah. And maybe so I will not speak of the other open questions because I did not speak at all of quantum ergodicity, but I really have to stop. Thank you.